Welcome to Study Loop.
You've clicked on question 27.20 about the motion of charged particles in a magnetic field. This is an application question, so I'm going to give you a bit of background to help you understand what they're asking for. This question refers to a cyclotron. These are commonly used in physics to accelerate particles by confining them to a ring. As a particle travels around the ring, boosts are applied using an electric field, and circular motion is tuned using a magnetic field. Let's look at the problem parts. Part A asks us to find the speed of a 5 electron volt hydride ion. We can write this as H minus. So H is going to denote the atomic mass, and the minus denotes the electron charge. So there are two things we need to identify here: what information the problem is giving us and what they're asking for. The cyclotron starts with a linear accelerator stage called an injector. But even if you didn't know that detail, you can see that part A has given you a potential energy U of 5 MeV. I'm going to stick that in our important numbers over here. U is 5 MeV. So this comes from the fact that our particle has experienced a linear electric potential, causing it to accelerate. If you want to brush up on this or the units electron volts, go back to chapter 23.2, electric potential, and look at the equation 23.12 in the 14th edition book. Okay, since we're on the same page, we're going to convert this potential energy U into kinetic energy. Let's use energy conservation. So we have that our potential energy is going to be equal to a kinetic energy, and the kinetic energy is written by 1/2 mv squared, where v is the speed of our particle. So now we have an equation that relates our potential U here and our velocity. Let's solve it and rearrange this to get the actual number. So the first thing we want to do is multiply this 2 over. So we have that v squared is equal to 2u, and we're going to divide that by m. Now we have to take a square root of both sides, and that gives us that v is equal to the square root of 2u over m. Since they've asked us for the magnitude of the velocity, we can drop the sign and write this equation in terms of the numbers that we're going to plug in, as we see here. So this is our final equation. Now we have to start dealing with the numbers in the problem. Here we want to be especially careful because we're using electron volts, not joules, as energy. These units won't give us speed in meters per second, which is what they're expecting. So we need a conversion factor. We have that U is equal to 5 MeV. And now we're going to multiply this by a conversion to joules, which is a fancy number 1. So this is like multiplying by a fraction that is going to be unity, or the number 1. So we're going to multiply this by 10 to the minus 19th joules per electron volt. And that gives us a final answer of the potential in joules of 8 times 10 to the minus 13 joules. Now we need one more number. That would be the mass of the proton, since this is a hydride ion, or an H, or hydrogen. That means that the mass of the proton we have to look up, and I've done that right now. It is 1.672 times 10 to the minus 27 kilograms. All right, so to finalize this, we're going to need to plug these numbers into our formula. So we have that v is equal to the square root of 2u, and u is 8 times 10 to the minus 13 joules. And then we're going to divide this by the mass, and our mass is 1.672 times 10 to the minus 27. All right. This will let us actually calculate. If you plug these numbers into a calculator, you'll get the final speed of 3.09 times 10 to the 7 meters per second. And then as a sanity check, we see that this is not greater than the speed of light, which is 3 times 10 to the 8th meters per second. So that concludes part A. We're going to switch out now gears into part B and see what it's asking. Again, we need to identify what information will be relevant. So B is placing the charged ion from the last part in a perpendicular magnetic field. This actually makes that charged particle go into an orbit, and that magnetic field in question here is B equals 1.9 Tesla. So now we're going to need to write that in our important numbers. B equals 1.9 Tesla. Okay, so how are we going to get from a magnetic field to a radial motion? So we actually know from earlier in this chapter, 27.2 and 27.3 actually, that a magnetic field exerts a force on a particle. It's always normal to the velocity of this particle, and we have that the magnetic force is equal to Q V B. And again, that was 27.3 in your book. So as you all may have remembered from mechanics, we have Newton's law. That says that the force is equal to ma. What you may not remember, so I'll refer you back to chapter 5.4, is that in circular systems, we can have a special relation for the acceleration. So that's a radial is equal to v squared over r. That's the circular radius that our thing is orbiting in. And so that was equations in 5.4 again. Combining these together, we can actually write out an equation that relates our velocities, our B field, our charge of our particle, and the radius. So now we have F equals ma, so that's m. We're going to use our radial acceleration, so that's v squared over r. And we're going to set that equal to our force, which is qvb. Now, what we're looking for is the radius. So let's cancel out one of the velocities. Cross multiply. So that's going to bring our r up. So we have r, q, and b on one side is equal to mv. And now we're going to divide out and get that r is equal to mv divided by qb. So now we have an equation for r. We're going to go to our numbers step. Our important numbers that we may have remembered from the previous part was the mass of the proton. So the mass again was 1.672 times 10 to the minus 27 kilograms. We have the velocity from the previous part. That was 3.09 times 10 to the 7 meters per second. And now we have an additional number, which is the charge of our ion, and this is a single electron. So we're going to put our electron charge Q is equal to 1.6 times 10 to the minus 19th coulombs. Now that we've done that, we're going to plug all these numbers into our equation here. So we have that R is equal to the mass, 1.672 times 10 to the minus 27 kilograms. The speed, which is 3.09 times 10 to the 7th meters per second. And last but not least, we're going to divide by the charge and the B field. So the charge was 1.6 times 10 to the minus 19th coulombs. And the B field here was 1.9 Tesla. So if you've been following along and plugged all these numbers into your calculator, you're going to get the final answer of 0.17 meters. So that's 0.17 meters. and that's the radius of our cyclotron. This concludes our coverage of this problem. If you want some additional practice, I would suggest doing the problem again with a charged helium ion, and we'll make it a helium +2 ion. So that way you have to take into account a new atomic mass and a new charge. Good luck on that. I'll see you in the next video.